So this is going to be a titration problem. And so titrations are a really big concept. And so you do want to make sure that you, you want to make sure that you guys have an understanding about your titrations. So it's giving us a reaction above. And it's saying that 34.0 milliliters of HCl is required to neutralize 25 milliliters of caffeine. What is the concentration of the caffeine sample? Now, is caffeine going to be an acid or a base? What do you guys think? We should definitely know that caffeine is going to be a base because it tells us right here in the question. We could also have figured out from our reaction here, as we're producing that hydroxide, which is going to be a base. And so when we look at this base, how many acids does it take to neutralize this base? Right? So how many of these protons can it pick up? And so if we look at our reaction down below, we can see that our caffeine picks up 1 hydrogen. And so it's going to need 1 acid to neutralize it. So when we're going through this titration, this neutralization, what we want to do is neutralize means to set your mole of your acid equal to your moles of your base based on how many they can neutralize. So if you have an acid that's diprotic, then it releases twice as much H+. If you have a base that's can take on just 1, then you can only bring out 1 mole of your H+ from it. And so we're trying to set those equal to each other. So right now, we want to start with what we know. So use the side that we know all of the information about. So in this case, this is going to be our acid because we know the volume of it. We also know its molarity. And so we're going to start with that part first. So we're going to take its volume. We're going to convert it into liters. And then I'm going to change that over into moles of my HCl. So 0.025 moles of HCl for every 1 liter of solution. And for every 1 mole of HCl, I need 1 mole of caffeine. Now we know the volume of that. And so we're going to be able to plug that in that next part. So I'm just going to stop there for now, and I'm going to find out my moles of my caffeine. And I know it's a 1-to-1 ratio between them because the HCl releases 1 H+, it's a monoprotic acid, and the caffeine takes on 1 base because we saw that through that equation above. So now I have 8.5 times 10 to the minus 4 moles of my caffeine. And if I want to find the concentration, then I just need to change that to moles per liter. So I need to take my moles, 8.5 times 10 to the minus 4. And I can divide it by my volume, 25 milliliters. I just need to change that to my liter. And we get 0.034 moles per liter, or molarity. And that's what we're looking for. Does anyone have any questions on that part? So you could have given me other answers right? So you could have given me a different concentration unit. So you could have done like moles per kilogram, things along those lines. But for the way that we have it set up, moles per liter is going to be the one that makes the most sense, right? Because they're giving us a volume of a solution, then it doesn't really make sense to use it in any other way because we have the moles of it, but you could have given me another type of concentration unit. So it just depends. For your final on your ACS, we generally dictate what units we're looking for them, right? And so a common one is molarity. Yep. Mm-hmm. Okay, what question would you like to go over? So when you have a question where you guys are looking for the amount of carbon by mass of a hydrocarbon, there's a couple of different things about it, right? Now, when it's saying 84.1% by mass, what that's saying is that if you were to have 100 grams, 84.1 grams would be carbon. And then the rest would be hydrogen. So what you want to do is you want to look for something in your options that has that same amount of carbon compared to its total molar mass, what would be 84% of it. So if we have options like C3H8, what you can do is you can find its total molar mass. You can find the mass of only the carbon. And you can see if it lines up with your 84%. Right? So this is the fastest way, or maybe not the fastest way, but this is one of the options. So C3 is 3 times 12 plus 8 times 1. So we have a total molar mass of about 44 grams. 36 of that is carbon. So 36 divided by 44 is 81.8%. Now that's not quite 84.1%. So we would probably want to try some other options to see if there's a better one to match our 84.1%. There's a secondary way to solve a problem like this, where once we have these 84.1 grams and this 15.9 grams, we can find its empirical formula. So that means that we divide each of them to turn them into moles. And once we have the moles of the carbon and the moles of the hydrogen, what we can do is we divide by the smallest number here. So between our two options, our moles of our carbon is our smaller one, so we divide by 7. We take our 15.77, we divide that by 7 as well. So this becomes, bring this down here, a ratio of carbon is 1, and our hydrogen is 15.77 divided by 1. Or sorry, 15.77 divided by 7, which is about 2.25. Now, 0.25 that to me lets me know that that should be about 1/4 is 0.25. So if I multiply this by 4 and this by 4, we're going to get a whole number. And so I can see that for my formula, I'm looking for something that's close to C4H9. So something with that same ratio. So it could be C4H9, it could be C8H18, it could be C12H27, but all of those would have that same ratio of my 84%. So it depends on which way makes the most sense to you. You can find something that has 84.1% by mass. You can find the empirical formula of it. Or you can basically do a guess and check type of scenario. Does that clarify that question for you? All right. Okay. Now, this question is looking a little bit about resonance here, right? And so we have nitrous oxide, N2O. And so we want to create our best Lewis structure from here. And then we want to think about which one is going to be our best option for it. So when we look at this, between nitrogen and oxygen, nitrogen should go in the middle. So we can put an oxygen on one side and nitrogen on the other. We should have a total of 5 times 2, so that's 10 plus another 6 electrons. So we have 16 valence electrons. We're going to start with our oxygen first. So that's 2, 4, 6, 8, 10. So we got 6 more left over. 1, 2, 3, 4, 5, 6. And now we want to start to kind of fill in. So we've used up all of our valence electrons. We can see that we're still short electrons in the middle, right? It doesn't have a complete octet yet. So we need to move some electrons from the outside into double bonds, right? So we have 2, 4, 6, 8, 10, 12, 14, 16 electrons there. We need 4 more on the middle. And so we can choose to do that by taking from our nitrogen and making that a double bond. So there's one set. Now we can look at our next one and we can think about, well, do we want to take more from that nitrogen or do we want to take some from that oxygen? How are we going to make that happen? So I can set this up like this one here with a triple bond. Now, if this is a triple bond, then we're going to have for 4 more charges, this one will be neutral on that nitrogen. This is going to be, the central nitrogen is going to be 5 minus 1/2 of 8. So it's going to be a +1. And this oxygen on this right-hand side is going to be a -1. If I go backwards and I take it from my oxygen instead, that nitrogen in the middle is still going to be a +1, but this time our oxygen is going to be 0 and our nitrogen is going to be a -1. And so we're trying to figure out between those options, which one is more likely to happen. The problem with this setup over here on the top right is that this central one, or sorry, not, this one over here doesn't have a complete octet. So we're going to try to complete all of our octets. And so we're trying to figure out which of those 2 options is kind of our better one, our D or our A. So both of them have the same amount of formal charge in that we have a +1 charge and a -1. The difference is whether it should be the oxygen that gets it or whether it should be the nitrogen. So which one's more electronegative, the oxygen or the nitrogen? What do you guys think? oxygen's more electronegative, right? Is closer to that fluorine. Your fluorine is your most electronegative, so it increases going to the right and going up your groups. So does that make it more likely or less likely to have a negative charge? If you're more electronegative, or you're more likely or less likely to get the negative charge?
More likely.
More likely. And so that's why A is going to be the one that does our most, that contributes the most to your resonance. So when you're asking this type of question, it's looking for your most stable option. It's kind of like your best Lewis structure. Because if they just were to ask you only for Lewis structure, you really could have drawn all of these. It's just that things like B and C are really not that likely to occur. And D does show up, but not as much as A. And so that's why they phrase it the way that they do, is so that way you can tie those two together. Now, drawing Lewis structures is a really important thing for the second half of our class, right? You need to make sure that you can do a Lewis structure, so that way you can find your Vesper shapes. And that way you can find your intermolecular forces, because both of those won't end up correct if you can't do a Lewis structure. So remember, there's 5 steps to doing the Lewis structure. 1 is you need to know your number of valence electrons. 2, you need to choose your central atom. 3, then set up the bond skeleton. 4, you want to populate the lone pairs. And then 5, make multiple bonds. And then the last part is going to be 6, and that's where you check it. So keep that in mind. For me, I personally think that Lewis structures is kind of like naming. Doing them is going to be your best bet for that. It just takes some practice in order to do them quickly. Once you start to use them often, you'll be able to see things like, well, most of our nitrogens do make triple bonds, right? The thing about that, though, is those are just general rules, which is why I don't teach them to you. Because like how oxygen generally makes a double bond, it doesn't always, as we can see here. Right? But the more you do them, then the more confident you'll be able to see what they normally behave like, and also be able to predict when they aren't going to do that. Okay. All right. So that sounds to me like you're looking for a balancing equation. So if we were going to set up something like this, now there's 2 types of things that you need to balance, right? Sometimes you just get the equation as a word, and sometimes you get it as they've written it out, and then you need to balance it out. So let's say that we have a sample of calcium carbonate. And we're going to decompose this into calcium oxide and carbon dioxide. Right? So if they want that balanced chemical equation for that process, the first thing that you want to do is you want to translate those words into their chemical formulas. So calcium carbonate, CaCO3, calcium oxide, CaO, carbon dioxide, CO2. So now we know that calcium carbonate decomposes, so that's our reaction arrow, into calcium oxide and carbon dioxide. So this is the one where we used to list out the elements of what we had inside. So we used to list the element. We would write how many we had. So we had 1 calcium, 1 carbon, 3 oxygens, 1 calcium, 1 carbon, 3 oxygens. And then we used to change the coefficients in front to make those equal. Now I realize this was a bad example because it's already balanced for us. So the coefficients in front of all of these are 1. But we can look at a different one, and then we can work through and balance that equation there. Let's say that we have let's say that we're doing this decomposition instead, right? If we want to balance this equation, then we need to go through and we need to look at each of those elements, the number of atoms that we're getting, and then we need to adjust the numbers in front in order to make those balanced. So if this is my calcium, my nitrogen, my oxygen, this is my calcium, my nitrogen, and my oxygen. Let's say for the right-hand side, we have 1 calcium, 1 nitrogen, and 4 oxygens based on how it's written. How many calciums do we have in our reactant side? 1. How many nitrogens? Not just 1 nitrogen, because we have that 2 there. So we should have 2 nitrogens. Remember that those numbers outside the parentheses goes to everything inside. How many oxygens do we have? 6. Very good. So are we balanced looking at it as it is right now? No. All right, so we do need more. So the first one I like to start with is my calcium because they're already balanced. So I just know that that ratio, whatever number goes in front of this set on the left, has to show up for the one on the right as well. So my calcium's all balanced. Now you have a choice. You can do either your oxygen next or your nitrogen. Which element do you guys think we should do next? Our oxygen or our nitrogen? Definitely the nitrogen, right? And the reason for that is our nitrogen only goes from one to another. Our oxygen, when we balance that, kind of goes through this chaotic process where it's got 2 different things that it can go into. So we're not going to do our oxygen next. We're going to do our calcium or our nitrogen because there's only a 1-to-1 of it's in one substance on the left, one substance on the right. So what number do I need to put in front of this NO2 to make this balanced? If we put a 2 in front of this, then that makes this nitrogen 2, and it makes our oxygen, we have 2 times 2, so that's 4, plus another 2, 6. And so are we balanced now? Right? And now we're all balanced. And so that was the nice part about doing the nitrogen, is it balanced us, and so now we don't even have to worry about finding the ratio for our oxygen. But if oxygen wasn't balanced, then we would be looking at modifying those ones in order to get those numbers to work themselves out. So this is called balancing equations, and that's how you get those coefficients. Does anyone have any questions on that part? There's one other thing that you want to think about when you guys balance equations, and that's in these special circumstances where you can have something that looks a little bit like this. When you look at this equation here, does this equation look like it's balanced? When we first look at it, it looks like it's balanced because we have one calcium on each side, we have one zinc on each side. But there's something that's kind of funky going on here if we pay closer attention. If you look at this calcium is changing from a 0 to a +2. And this zinc is going from a +1 to a 0. So what kind of reaction is this an example of? What kind of reaction does this one look like? If this calcium is going from a 0 to a +2, and the zinc is going from a +1 to a 0, the charges are changing, and so the number of electrons are changing. So it's not necessarily a precipitation because we start with a solid and we still get another solid out, right? A precipitation, normally you, I mean, in some ways, I guess you could classify it because we are getting a new solid out. But most of the time with our precipitation, that's when we have two solutions, and then when you mix them together, you get a new solid. This is a redox reaction. Very good. And that's because we have a reduction occurring and we have an oxidation. So when our calcium is going from a 0 to a +2, is that going to be a gain of electrons or a losing of electrons? So is calcium gaining? So calcium is losing electrons. And in this case, it loses 2 electrons. And our zinc is going to gain 1 electron. So just as a reminder, if we gain electrons, are we the reduction or the oxidation? Reduction. Very good. Because your charge is reducing, so you're the reduction. If you lose electrons, you are the oxidation. So we have NOx in red cat. So anode is where we have oxidation. Cathode is where we have our reduction. So for a redox reaction, the other part to remember is we do need to balance our number of electrons. So we need 2 zincs and 2 zincs here. So that way we do this twice. So that way our electron count is also balanced. So that's the one caveat to balancing your chemical equation, is sometimes it doesn't just stop because your atoms have balanced out. Sometimes you'll continue on past that point because you need your electrons to balance out. So the things to look for is whether it's called a redox reaction. The second thing to look for is you'll notice that the charges beforehand weren't balanced. We had a +1 on the left, we had a +2 on the right. Now we have 2 +1 ions, so that becomes a +2, and we have 1 +2 ion, and so now our charges are balanced. And so that's a way to check those things if you're not sure. Anyone have any questions on that part? Okay. Then let's get back into this one. Now, there's some questions about sigma bonds and pi bonds. To do this, you have to be able to draw your Lewis structures. Just remember that a sigma bond, there's one sigma bond in a single bond. In a double bond, how many sigma bonds are there and how many pi's? So if we have a double bond, how many sigma bonds is it is 1 sigma and 1 pi. And so a triple bond is still 1 sigma and 2 pi. So if we look at this just very briefly, all of those that I drew out right there are our sigma bonds. We know that that bond skeleton that we make has to at least be sigma. On top of that, what we notice is we actually have 2 double bonds in there. So we should have 1, 2, 3, 4, 5, 6 sigma. And then we should have 2 double bonds. So each one gives me 1 pi. And so that should be 2 pi bonds. And so we're looking for C there. So just a reminder about that, about where your sigma bonds are versus your pi. Pi bonds always happen when we have double bonds. Sigma bonds when we only have 1. All right. Now, this is the other one that I really want to make sure that we go over. I think that this is an important problem because it's dealing with our theoretical yields. And so if you haven't tried this problem, this is definitely something that I would recommend. Right? So as you go through this, we kind of have to piece together our reaction, and then we're going to have to calculate our yields. So this is the Haber-Bosch process. It's a really important process in real life as well. And so we're going to take nitrogen gas, and then this should be and hydrogen gas. So nitrogen gas should be N2 plus H2 to form nitrogen trihydride, so NH3, which is also a gas. And so whenever we start this, then we need to balance this out. So we're not balanced as we are here. So what coefficient should go in front of our hydrogen in order for this to become balanced? What numbers should we have in front of that H2 to balance this out? And what number should we have in front of our NH3? That becomes a 3. This becomes a 2. Very good. So anytime you guys have these theoretical yield problems, anytime you're going to try to make something out of your materials, make sure you balance your reactions. Because if those aren't balanced, then your numbers are always going to be funky as you go through it. So now it's telling us that we have 56.506 grams of nitrogen. And we have 19.047 grams of our H2. And then they want to know how many grams of that NH3 can we make. So if we have 2 reactants, how many equations or how many times do we need to do this calculation to figure out our theoretical yield? Right? So if we need to figure out our limiting reactant,
2.
we have 2 of them, so we need to do it twice. Very good, Brian. So if we have them in grams, whenever we have grams, if we're going to compare something, we have to get them into moles. Once we go from our moles, then we can use our balanced equation to get them to moles of product. So this would be our moles of our reactant. And then once we're in moles of product, we can turn it into grams of product. All right, so that's kind of like our pathway. So we're going to set up one of these for our nitrogen, which is going to be 56.506 grams of N2. And we know that 1 mole of N2 is 28.0013 grams. And we know that 1 mole of our N2 is 2 moles of our NH3. And we know our NH3 is 14.00674 plus 3 times that of our hydrogen. And so we can plug that through. And we get 68.7059 grams of our NH3. But we have to do it also for our hydrogen. That equation for the hydrogen looks pretty much the same. We have 19.047 grams of hydrogen. 1 mole of hydrogen. The only difference is we have different molar masses for it and a different ratio. And so we should use 3 moles of hydrogen for every 2 moles of NH3. This part stays the same though, because we have the same molar mass for our NH3. And so this becomes 107.28 grams NH3. The 17 is just our molar mass of our NH3. So that's 1 nitrogen and 3 hydrogens added together. So this is the molar mass of our H2. This is our molar mass of our NH3. So whenever you're going from grams to moles or moles to grams, you're always using your molar mass, and you're going to get that from your periodic table. All right. So between these two values, which one is going to be our limiting reagent? Is it going to be our ammonia, or is it going to be our, is it going to be our nitrogen, or is it going to be our ammonia? What do you guys think? Which one of these limited us? So ammonia is what we're making, but what we're looking for is between our N2 and our H2, which one is our limiting reagent? So H2 made 107 grams of our NH3. Our nitrogen only made 68. So our hydrogen shouldn't be our limiting one. Even though it's the smaller amount of reactant material, because of its molar mass being so much smaller, it actually ends up being more abundant than the N2 in terms of moles. And so we don't want H2 to be our limiting. Our limiting is going to be our N2, because it gives us the lowest yield of the ammonia, the NH3. So now it's asking us, well, if we made our actual yield 66.02 grams of NH3, what would our percent yield be? We need to take that, we need to divide it by our theoretical, 68.7059. Multiply that by 100%. And we get something like 96.1% yield. You guys have any questions about how we got all the way to our percent yield? Now, for the follow-up question for it, the one where it's asking us about the how much of each reagent is left over. I'm going to assume that you guys would be able to figure out, right, how to go back and do that part, or at least you can find how to do that one. I think there's a couple other things I want to touch on first before we kind of get into that. So if you don't know how to do that, we can always go over that this afternoon during my next review session. Right? The other part that I kind of wanted to walk over with you guys is our ideal gas. So let's say that we had 66.024 grams of NH3. And let's say that this was at 130 degrees Celsius. And the pressure of 2.30 ATMs. What volume of gas did we recover? So whenever it's asking us for something about the gas, whether it's our temperature, our pressure, our volume, there's an equation that should spring to mind when we're solving that. And that's PV equals nRT. So we want PV equals nRT. And so it wants us to solve for our volume. So our volume is going to be nRT over our pressure. And so we need to do some conversions here. And you're right, we need to get our NH3 into moles. We also need to get our degrees Celsius into what? Kelvin, right? So let's turn our 66.024 grams into moles, so 17.03. This becomes 3.8768 moles. 130, we just need to add 273.15, so this becomes 403.15 Kelvin. And then we can plug that in. So this is our 3.8768 moles times our R, 0.08206 liter atmospheres, K mole, temperature for 3.15 Kelvin, all of that over 2.30 atmospheres. And if we look at this, we can see that our moles canceled, our atmospheres canceled, our Ks canceled. So we're just in our liters, which is what we're looking for. So our volume should be 55.76 liters. Do you guys have any questions about that part? Now, there's a lot of things that you guys can do with ideal gas. Right? There's things like this where you're really just plugging into the equation, so you're just rearranging the equation. The big one is make sure that when you solve for N, it's not RT over PV. N is PV over RT. Right? So that's one. The other one is you should be able to do what we call as a combined gas. That's where you have one sample, but you change its conditions. So you might not know all of the information, but you know that you have it at one temperature and at a second temperature. And so you're looking for the pressure in relationship, but you might not know everything else. You might not know the volume of it. You might not know the moles of it, but you just know it's the same sample. And so you want to make sure that you can practice with those. And then the last part about that is if you have a mixture of gases, that they're made up of the sum of their parts. So that could be either the pressures, but it could also be the number of moles. And that's called Dalton's law of partial pressure. And so that's the other type of problem with ideal gases that you want to pay attention to. Now, in the slide pack, there are some examples of that. This one here is looking at getting our densities from a couple of different mixtures. So you have to look through that. And then I believe we have one other one in here where we look at our amounts of materials as well. Right? So that's definitely something I would recommend that you go over if you haven't done it before. You can also think about capturing gas above our solution. There's a worksheet in your extra resources section where you guys can kind of practice that as well. So if you don't remember how to capture a gas above a solution and what that looks like, then you can use that kind of like as a good refresher on your ideal gas stuff. But we're pretty much coming up at 9 o'clock, and I know that you guys have the ACS exam at 9:30, right? That email with the access code will go out about 9:20 or so. And so I want to open this up if you guys have any other questions, but we won't go through any more. I'm not going to just randomly go through a problem just because I want to make sure that you guys get enough time to mentally prepare yourself for the ACS. So if you have specific questions, I'm more than happy to answer those now. Otherwise, we'll also do this review. I'll do this review this afternoon from 1 to 2:30. And then I'll post that up on YouTube.